Hello everyone, my name is Pravin Mariappan and today I'm going to give you a video presentation about the study on the effect of critical fluid parameters on the separation efficiency of horizontal two-phase oil and water hydrocyclone separator. This study was conducted by the Shelby Company Limited, which consists of our project leader NANTHAR KUGARN, DHARMESH Kumar, Michael Davis and myself. This study is part of the requirement of the flow assurance subject and is supervised by Dr. Jundika. Next, let's take a look at the presentation outline. I'll be giving you a brief introduction about hydrocyclone and how it works, and also the problem statement and objectives of this study before handing it over to my colleague Michael. Now let's take a closer look at the hydrocyclone. The hydrocyclone is a simple and effective equipment that has enhanced separation efficiencies when compared to conventional separators. It consumes a smaller space, thus increasing the process efficiency per unit volume. This device was first designed in 1891 by Bradney. An important aspect of this equipment is that it has no mechanical or moving parts because it works on the principle due to the centrifugal forces and the difference between density and viscosity of the fluids involved. Now let's look at how this equipment works. So first, the water or the crude oil is fed into the inlet, which is here. And the shape of the inlet induces a high fluid spin, resulting in rapid formation of a vortex. So when this happens, centrifugal forces causes the denser water to concentrate on the outer diameter, which is around here, and also the lighter hydrocarbon phase to collect in the center of the equipment, which is here. So this low density of enriched phase can be removed from the center of the hydrocyclone head in the reject phase. Now let's take a look at the problem statement for the study. So conventional separator takes a very long time for liquid-liquid separation, particularly oil-water separation. Hydrocyclone has been innovated to reduce the separation time, but not all mixtures gives continuous separation. The current hydrocyclone in the market have different separation efficiencies for each platform, even for the same model of hydrocyclone. This is due to the differences in the fluid properties. That is why our objective is to study the effect of critical fluid parameters on the separation efficiency of horizontal two-phase hydrocyclone separator. Therefore, our scope of study will include identifying and investigating the effect of velocity on flow, density and viscosity of crude oil, and also the oil-water ratio to the separation efficiency. After that, we'll employ the Taguchi method to determine the optimum parameter for flow to improve separation efficiency.
Hi, my name is Michael Davis. I'll be briefly explaining in our literature review. So firstly, we have the study of separation in a two-phase flow, in a multi-phase flow. Okay, the next we studied on the designs and equations used in CFD modeling of hydrocyclone. Next, we also studied on the crude oil parameters such as API gravity and the viscosity, how it affects the flow. Lastly, we study on the types of hydrocyclone geometry to understand which type of geometry gives us the best efficiency, the maximum efficiency. So from there we choose our best geometry for our hydrocyclone. Alright, thank you, that's all from me.
Thank you, Michael, for the presentation on the literature review. So now I'll be talking about the methodology of our research. So we start off by identifying the critical fluid parameters based on research, and then we identify the design of hydrocyclone and design it in the ANSYS workbench. Then we add our boundary conditions for our analysis, and also we perform a design of experiment to determine different combination of parameters and also to do optimization of which parameter and how it affects the separation efficiency. Next is the hydrocyclone design. So as for the hydrocyclone design, we're using the Coleman and Thew model, where we use a single inlet horizontal hydrocyclone. This is our model based on the Coleman and Thew model. This is in ANSYS. And next is the meshing. So as for mesh, we are able to achieve 498,000 mesh, which is almost the close to the maximum of mesh we can achieve in student version of ANSYS, which is 512,000. So we did slicing and also division of the mesh size in order for us to achieve this maximum mesh of 498,000. And this is the meshing. So as for aspect ratio, a good aspect ratio should be below 10, and 90% of our design have a meshing of aspect ratio of less than 10, while there are some minor parts that have a max of 41 aspect ratio. This is due to the complexity of part, like the inlet of the hydrocyclone. Next is skewness. The rule of thumb of skewness is the skewness value should be below 0.7 for good skewness, and we are able to achieve that. About 90% of our design we are able to achieve a good skewness. There are some parts which are above 0.99, 0.7 because of the complexity of the part as well. Then I would like to go to a boundary condition. So the reason why we use Taguchi's method design of experiment, because of it is a robust model and it's a good software for optimization because it uses less number of experiments for more factors. So how do you determine the performance efficiency is by finding the signal to noise ratio, and also we can use analysis of variance to determine percentage of each parameter's contribution. This is our processing parameter, and this is the combination of processing parameter with the Taguchi's design experiment. Next, we use Reynolds average Navier-Stokes standard K epsilon model because it is useful for parametric study as it requires shorter time for simulation. And finally, we analyze the wall function where based on our mesh size, which is 15 millimeter per mesh height, we are able to get y plus of 42, which is between 30 to 300. Thus, we can use a standard wall function. Next, I would like to pass the floor to Nanda for the results and discussion.
I'm Nanda, and I'll be talking about the experiment results on this part. So this is the experiment results for simulation 1 for viscosity 0.01, oil water ratio 70:30, velocity 10, density 500. So these are the results. So at outlet 2 is 100%, oil at outlet 1 is around 36%. So this is the result for simulation 2. Same thing. Simulation 3, simulation 4, simulation 5, simulation 6, simulation 7, simulation 8, and simulation 9. So based on these 9 simulations, we can now do the analysis of results. So in order for us to do the analysis of the results, we need to first evaluate the system performance. So we're going to evaluate the system performance based on 2 things. So we're going to give scores based on 2 things. So basically we have the oil volume fraction at the expected oil outlet and the oil volume fraction at the expected water outlet. So logically, obviously, so the higher the oil volume fraction at the expected oil outlet, the higher the score given, and the lower the oil volume fraction at the expected water outlet, the higher the score given, because we want the higher oil to come out at the expected oil outlet and lowest oil to come out at the expected water outlet. So based on that table just now, this is how we this is the scores given to each experiment. So experiment number 5 is the best result so far because it has 20 and 19. So this means it has the highest oil outlet, and highest and the lowest oil at the water outlet. So based on the 2 scores just now, the 2 scores are then fed into this table and then it's fed into the Excel software. The Excel software then calculates the signal to noise ratio for us. This signal to noise ratio is then used to calculate the effect of each critical parameters on the separation efficiency. We have 4 critical parameters: the velocity, the density, the water to oil ratio, and the viscosity. So the effect of oil viscosity and separation efficiency can be seen in this graph. So we can see that 0.01 is the lowest, then it increases to maximum at 0.1, and then it reduces, the separation efficiency reduces at viscosity of 1. So from here we can see that we have reached the optimized oil viscosity of 0.1. So anything other than 0.11 will not be so good. So same thing for the oil to water ratio. The best oil to water ratio is 50-50, as there's a peak in the graph, and anything other than that will not be so good. So it's not the same for the velocity, however, because in this graph is a steady graph. You can see that the higher the velocity, the higher the separation efficiency. This is in par with our literature, which shows that the higher the flow rate or drift velocity, the better the separation efficiency due to the impact in the separator and dispersion of the fluid. Okay, now the density, however, we can see that 500 at density of 500 has the highest separation efficiency, and 900 has the lowest, and 1300 is somewhere in the middle. So the correct way to read this graph is that the lower, as you can see, this line is actually the density of water. So the lower the difference between the density of oil and the density of water, the lower the efficiency. For 900, the difference in density is only 100. So we have the lowest separation efficiency. For 1300, the difference in density is 300. So we have slightly better separation efficiency. And for 500, the difference in density is around 500. So it gives the best separation efficiency. So this is the combinatorial effect of the separation efficiency. We can see that density of oil affects around 78.7% of the separation efficiency. Therefore, the density must be taken into account when designing a hydrocyclone separator. Followed by the velocity of the mixture, which affects around 10%. If the velocity is too low, we can always boost it up with a pump. Viscosity, we can always viscosity and ratio of oil, they play very small part, but nevertheless they must be considered as well. Viscosity, we can always play around with the temperature to make the viscosity higher or lower. As for the ratio of oil to water, we have to play with the geometry of the hydrocyclone separator itself to make it longer in case the oil ratio is higher. So optimized fluid parameters, based on our findings, we have found the best values for all four parameters. So we will use the best parameters, well, the best values for all the four parameters, and do another simulation to validate our results. So this is simulation number 10. So using the highest viscosity, highest density, highest all the four parameters values that give the highest value of separation. So we use that to run simulation 10, and this is the result we got. The four parameters and simulation number 5 had the same parameters. This is purely coincidental. So this is the animation that shows the separation of oil and water. Phase 1 is oil, so the red color will show oil. So we can see the separation after a while, and there's oil coming out here, or full red coming out here, and blue all the way down here. So this animation shows only oil for simplicity reasons. So we can see, since our concern is only oil, so we can see that oil is coming out around here, and after some time we do have some oil slowly leaving the other outlet, as can be seen in the graph. But however, the oil leaving outlet 1 is still around less than 5%, so it's still acceptable region, and this is the best result that we got. Thank you.
Alright, to conclude our presentation, we can say that we have successfully studied the effect of critical fluid parameters, namely viscosity, oil to water ratio, velocity, and density in the separation efficiency of the hydrocyclone separator. And also we use the Coleman 2 hydrocyclone separator model for this. So mainly what affects the separation is the density of the oil, which seems to have an effect of 78.7% of the separation efficiency, and thus the higher the difference between the oil and water density, the higher the separation efficiency. Thank you, that's all from us.